We present our work, Push the Boundary, Boundary-Aware Feature Propagation for Semantic Segmentation of 3D Point Clouds. This work is done by the Group of 3D Geoinformation and the Lab of 3D Urban Understanding at TU Delft. 3D semantic segmentation aims to assign per point a semantic label, for example, window, wall, road, and water. It is important for many applications such as urban modeling, autonomous driving, environment monitoring, etc. There are two main directions to tackle 3D semantic segmentation. First, traditional methods use handcrafted features to achieve segmentation. On the contrary, learning-based methods train a deep neural network to learn features from the input. Recently, point-based networks, especially point convolutional networks, have gained a lot of attention. They have achieved great success over many public benchmarks. However, the performance near object boundaries is not satisfactory. Motivated by this, our work aims to improve boundary accuracy of 3D segmentation. Here we show an example of framework of commonly used FCNs. It adopts an encoding-decoding strategy. Due to the feature pooling in the encoding and the feature upsampling in the decoding, information is lost at local levels, which results in blurred boundaries. Some works have been proposed to address boundary errors, such as BGENet, JSENet, and CBL. They either introduce additional loss terms as constraints or extra feature enhancement modules that are difficult to train. Instead, we jointly learn and use boundary priors to guide feature propagation in decoding. Our framework has one shared encoder and 3 streams. For each point, the boundary stream gives a binary prediction if it is boundary or not. The direction stream predicts a uniform direction vector pointed from the closest boundary to the current location. The segmentation stream predicts a semantic label. We fuse the outputs from the boundary and direction stream to guide the feature propagation in segmentation. Feature propagation happens in decoding, where high-level features from coarser resolution are upsampled to low-level features in finer resolution. Standard feature propagation with the features of neighboring points according to their inverse distance to the center in 3D space. This ignores the drastic semantic transition near boundaries. Instead, we combine the spatial similarity term WS and cosine similarity term WC to weight the features of neighboring points. This significantly encourages features to propagate along the desired direction near boundaries. We design our weighting term as a continuous function to facilitate backpropagation. We use 3 loss terms to supervise the 3 streams respectively. For more details, please refer to our paper. In the indoor dataset S3DNS, we report the performance comparison between the 2 baselines, PointNet++ and KBConv, and our networks. We train the networks using either 3D coordinates and colors or with additional normal information. We achieve improvements on all of them, especially in column, window, and board. Here we show the visual comparison using PointNet++ and KBConv backbones, respectively. From both comparisons, we observe consistent improvements near boundaries. We also report the segmentation performance on the outdoor dataset Sensat Urban using KBConv as the backbone. We train the network without normal information to achieve a fair comparison. We outperform all the competitors in the benchmark, especially in bridge, parking, and traffic road. The visual comparison shows that our method obtains more accurate boundaries. It also performs better in minor objects such as footpaths. Here we show our segmentation result in the videos. In the indoor scene, our method reduces errors on the wall. We avoid noisy segmentation on other categories, such as board and bookcase. In the outdoor scene, our method reduces errors on the roads and ground. We also detect footpaths with more regularized shapes. That's all. Thank you for watching.